All right. Hi, everyone. My name is Erica Fischer. I'm an assistant professor in the School of Civil and Construction Engineering. And I'm going to talk to you about all the timber and fire research that's happening here at Oregon State University, a lot of which is happening collaboratively with all of you and with other professors in this room. And so I'm going to just highlight those collaborations because I do think this is one of the unique aspects of TDI, that we are building all these collaborations across departments, across campuses, and between academia and industry. All right, let's see if I can do this thing. All right, so this is what I'm going to talk about today. I'm kind of trying to group all the research together. So we're going to start off in timber, concrete, composite floors, go to connections, and then talk about system level behavior. And then we'll finish off talking about all of the education and outreach that we've been doing, because behind, and as other professors have highlighted, behind all of this research are students. So we are educating the next generation of mass timber experts, so all of you can hire them. And so I think that's really important to highlight that part of our research and part of our work. But first off, we're gonna get a kind of timber and fire 101. So this is a massive misconception in the industry. So we're just gonna go over it real quick. Prescriptive fire protection design, that's when you open up the IBC and you pick out your hourly fire resistance rating, your 1 hour, 2 hour, 3 hour ratings. This only considers one fire demand. So it's a standard fire curve. That's how this is generated. You stick an individual building component or element into a furnace, expose it to the standard fire curve. When it meets a critical behavior threshold, the time it takes to get there is its hourly rating. This does not consider load redistribution. It doesn't consider any of the amazing topics of structural mechanics that we teach our students. It doesn't consider heat transfer through the cross-section. It is only just these very prescriptive requirements. On the flip side, we have performance-based fire design or structural fire engineering, and that's where we do actually use our knowledge of structural mechanics and structural engineering to design these structures. So we're looking at building-specific fire demands. What is the actual fire in the space? We're actually considering fire dynamics. We're looking at system-level evaluation, and we're considering load path. This is where the research is. So when we're talking about fire tests or we're talking about numerical models, we are not trying to get an hourly rating out of it. We're just trying to understand the fundamental mechanics of what is happening in this structure during a fire so that we can better design our structures to maintain load carrying capacity throughout the fire. All right, so to start off on timber, concrete, composite floors, this project has been going on for quite a while. We finished testing, we've done numerical modeling. There's a really great poster over here by a student, Julie Liu, on all the finite element modeling that has been done for this project. This is in collaboration with Andre Barbosa and Arishit Sinha, as well as a lot of industry collaborators. But one of the things that I want to highlight as part of this project is that we were able to establish collaboration with our friends to the north and in Canada. So all of our testing occurred at the NRC in Canada. We developed a really strong collaboration with them to share data, to share resources back and forth and information. We also developed a really great relationship with FP Innovations to collaboratively tackle testing and modeling of these floors and share resources across North America. And so we tested 2 CLT concrete composite floors, 1 NLT concrete composite floor, and 1 MPP concrete composite floor using different shear connectors. We did experimental testing in winter of 2019 and then last year in the fall. We tested 2 different generations of CLT, one that did not adhere to PRG 320 2018, and then one that did have the adhesives that adhere to it. So we could actually compare the results across the two different adhesive types. We were also able to take all that experimental data and compare it against empirical design methods. So, you know, what happens when we're using the elastoplastic method and gamma method for fire design? Can we actually use that? Is it applicable to all three of these types of floors? Is it applicable to floors with dowel type of connectors versus truss plate connectors? And then what Julie has been doing is all these finite element modelings of these floors, both heat transfer and structural modeling. So we were able to actually see through all of this that actually we're, you know, when we do finite element modeling in fire, first we model it without the fire. So we model it at ambient temperature. And we're able to see that we're looking at different behavior at ambient temperature than at elevated temperature. We're looking at different failure mechanisms. We might have rolling shear during fire. We might have tensile failure of the timber during a fire. We might have connector failure, or sorry, at ambient temperature. We don't have any of that during a fire. The connectors remain elastic. The timber remains fairly elastic. And so we're able to kind of compare across between ambient temperature and fire and see, well, if we're designing these at ambient temperature, then what are the detriments we're opening ourselves up to in a fire? And how do we actually design for that robustness during a fire itself? Okay, so I'm going to talk about connections a little bit. Lek already talked about this really great project that he's leading, but I'm going to start off with in glulam beam to column connections. We tested 5 different connections under deformation compatibility in the Richardson lab here on campus. These were 3 custom connections that we developed here at Oregon State University, and then 2 connections that were tested through sponsorship through MTC. And we were able to do 1 monotonic, 2 cyclic loading tests. I'm not going to present the results of this because this is the fire session, but I'm mentioning this because we're taking these connections and we're testing them in fire. So the point is so that there's deformation compatibility data and there's fire testing data for the same connections. Okay, so this is in collaboration with Ari Sinha, as well as industry collaborators with KPFF and Holmes. And again, leaning on those international collaborations. So we developed them, you know, 5 years ago, 4 years ago, testing the TCC floors. We're able to continue these international collaborations. FP Innovations is going to use the data from these tests to perform finite element models and then allow us to run parametric studies on connections, right? So the whole point is that we're not continuing to test every single possible configuration of glulam beam to column connections in fire. That's impossible. We want to understand the fundamental mechanistic behavior so that all of you can actually design these connections for maintaining load carrying capacity throughout the fire. Some of the connections that we're testing on the left is a knife plate connection. So the knife plate is slotted into the glulam beam. And then it is screwed into the column. And we're looking at, we tested this under deformation compatibility, where we have a notch that exceeds the allowable notch in NDS. So we're looking at what are those potential stress concentrations we could see at that notch. And now we're going to test it in fire. On the right is a beam to column connection where the beam is just slotted right into the column. There's really little mechanical connection between the two. We will be testing, we tested 2 versions of this under deformation compatibility, one with compressible insulation behind the beam and then one without. So what happens if you do have a gap and you can't get everything really tight? Can you put compressible insulation in there? What's the implications of that and the seismic performance? We're gonna look at that in fire as well. And the last one is 2 glulam beams sandwiching in one column itself, and with a steel bearing plate running between the 2. This connection has a lot of implications in heat transfer. So if we're threading a steel plate through the column, through both beams, we could potentially see some char propagation, some heat transfer propagation through that steel plate and into the timber itself. So this will allow us to really explore that. All right, so goal for this is, it hasn't happened yet. scheduled for the future. Stay tuned. Next year, I'll show you what happens. So this really, we want to look at the temperature distributions through the cross section. We want to gather enough data so we can benchmark these finite element models. So then we can also look at other behaviors. What happens if we reinforce notches with more screws? Does that create issues with heat transfer and accelerated charring, or does that actually help the strength of the connection during the fire? So stay tuned for this one. Like I already talked about this one already, but I did want to put all of the fire research together so you get to see really the full breadth of what is happening here at Oregon State University. In this testing, we were testing balloon frame and platform frame construction connections during a fire. And what TDI was able to do is provide supplemental funding to this grant to allow us to look at smoldering. So we have been testing a lot during the heating phase of the fire, but eventually the fire will go out, or the fuel will be consumed in the compartment. And then what happens? What is the subsequent heat transfer through the timber itself? Do we continue to see charring of the timber? How do we design these structures so that firefighters, when they enter the building, they feel comfortable and they can understand where smoldering may be occurring and where smoldering may not be occurring? So this is really critical to understand. So we were able to keep these specimens on the furnace for an extra hour. We shut the furnace off, we kept it on for an extra hour, and explore that heat transfer through the connections during the cooling phase of the fire. And what we found is we actually saw flames and combustion occur during the cooling phase. So these this picture on the right, that occurred 9 minutes after the furnace was completely shut off. So this is really, really important for us to understand and know how to design for, that we're still seeing heat propagate through the timber, even though there might not be combustion within the compartment itself. Okay, so timber concrete composite floors, you saw a little snippet of what's happening in connections. So to kind of looking at things elementally in a building. And now what I'm going to focus on is how do we bring it all together? So how do we actually model the whole compartment, the whole building together? And so in system level behavior, we've been looking at integrating BIM and fire dynamics simulator. There's a really awesome poster by Chi Sun over in the corner here. You should check it out. It's really amazing. And this is in collaboration with Yelda Turkin. She's a construction engineering management professor in civil engineering. And she's already developed methods to integrate BIM and time. So, we have a really big problem because we have this stipulation in the International Fire Code that doesn't allow us to have more than 4 floors unprotected as we go up a building. And so how can we actually design for the construction phase? How can we do fire design for the construction phase of the project? And what are the benefits or detriments of not following that, of actually violating that International Fire Code stipulation? So this is the goal of this project. But in order to do that, we need to simulate the fire itself. And that's where Chi comes in, it's just incredible doing this. So what we've been doing is benchmarking all the fire dynamics side of this integration against existing experimental tests. And we're able to actually simulate these compartments virtually through Fire Dynamics Simulator. We can actually simulate the energy being released over time in these compartments. We can simulate the temperatures in the compartments. We can simulate the airflow. And that allows us then to take that and integrate it with BIM, which is what we'll be doing over the next year. And actually look at the fire at different stages of construction. So when do we absolutely have to put in that fire protection in order to protect our property and an asset of the building? And what we found is that when we have this larger CLT exposure, we actually have a shorter time to flash over. It means that the fire engulfs everything in the room a lot faster when we have more exposed CLT. But it's not just about more exposed CLT. It's where is that more exposed CLT? And that's what we're able to do with FDS is we're able to actually look at, is the ceiling more critical? Are the walls more critical? Are the columns more critical? And how can we actually strategically apply our fire protection to minimize that fire impact on our asset, on our building? And then we are also able to look at, the impact of opening factors. So those are windows, right? So if we have more ventilation, then we can actually reach flashover really, really quickly, but it's actually, we have a shorter fire duration. So, we can look at all these different parameters to then and benchmark them against experimental tests so that then we can integrate that into the design process. All right, so the other full building kind of bigger scope is looking at life cycle assessment. So what we've been looking at is environmental impacts to these fires. And this is in collaboration with Ari Sinha in Wood Science. And we wanted to understand, some of you probably got our survey. We wanted to understand what are the biggest priorities if we wanted to be able to integrate LCA and fire? What are we missing? What research are we missing? What data do we not have? And what is the biggest priority? What's the most important thing for us to fund? And then we also asked ask people what is the likelihood that this will be completed by 2030. So see how optimistic they are about the research funding. So we were able to actually pull together some top research priorities in the field of LCA and fire. And what we found is really statistical data describing the number and severity of fires, looking on data of composition and physiochemical properties of building contents and assemblies. So then we can look at emissions data from the fire itself, and then looking at damage modes of structural components. And so this last part, right, kind of ties into these first two research projects that I was talking about, the TCC floors and the connections, right? We're looking at damage modes, being able to understand how these components are actually damaged in a fire so then we can design for them not to be damaged like that in a fire. And the second point here is where we're kind of going in our next project. So we've kind of identified in these three areas that we have really complex fire behavior in our compartments. We're seeing that the CLT itself is contributing to the fire in our compartment, which is then contributing back to our damage mode. So we have this cycle that we're developing. We're seeing that the structural behavior of our timber components is different in a fire than it is at ambient temperature. So we're not seeing the same damage modes in both. And we're seeing that combustion and charring is occurring during the cooling phase of the fire, as well as the heating phase. And then what we desperately need is to understand these emissions from the fire itself. And so this is where we're going in the future. So this project is being kicked off. It's in collaboration with USDA, with the EPA, with the Forest Service, and with ARIP to really look at LCA and fire, to look at smoldering, to look at emissions, to be testing components from small scale to large scale and develop data through scaling and understand, can you develop data through scaling? Can we test small components and have that be representative of the larger structure? Understanding what the emissions are from our actual building components with and without fire protection. What are the emissions that are coming off of our gypsum wallboard versus some more sustainable fire protection materials? So we have all these big questions and we're going to start answering them hopefully soon. Okay, so that's the research. But what I think is like the most impactful thing that we have done through all of this research are these people here. So we have trained and funded all of their educations and graduate educations through this research project. And they are now going and working for all of you. And so I do want to highlight all of these individuals and the opportunities that TDI has provided for them through this funding. But also, we can educate our students to go work as architects and engineers, but we also have to make sure people can actually build the building, right? So actually, at one of these events a number of years ago, I connected with the Northwest Carpenters Union, and they really wanted to train their apprentices in mass timber construction. And so we did just that. All of our glulam beam to column connection tests that we performed in Richardson Hall were built as a part of their framing class for their apprentices. And so they were able to actually learn how to build these structures with this material in a controlled laboratory environment, but also ask structural engineering students, ask structural engineering professors, all the questions they have about mass timber, about things that didn't even relate to these projects, and then come back and see them tested and understand the bigger, broader impact of what we're trying to do and understand through this testing. And then conversely, it was really awesome to watch the student have to answer all of their questions based on her drawings and her shop drawings that she made for them, which is a great learning exercise for a young structural engineer to go through. So I really thank the Carpenters Union for all they did. They built all our specimens for free, and it was just this incredible collaboration together. All right, so the second to last thing I'll mention in education outreach is that, we live in, Oregon is a lumber state. We have, and actually Oregon State University's School of Civil and Construction Engineering has 10% transfer students from community colleges. A lot of our community colleges are located in lumber towns. And so this is a mass timber webinar series, and TDI has supported this graciously. And it really highlighted the interdisciplinary nature of mass timber. We marketed it out to all the community colleges in Oregon, giving them a chance to see the opportunities in this industry for them through architecture, through construction, through structural engineering, through research, and what is out there for them as they kind of go through their program and hopefully transfer over here and continue their work. So if you want to check it out, the QR code works, and I'll take you to the website. All of the presentations were recorded. We'll be doing it again this year. If you think you have some really awesome speakers, let me know, and we'll definitely feature them. These are all the products that have been developed by the research that I highlighted today in terms of papers. This doesn't include all the thesis and dissertations that of the students. And then the last thing is looking into the future. You've heard a lot about this EDA grant. Part of this funding is to build a fire testing laboratory here at Oregon State University. And it's really exciting. This is an incredible opportunity. There are no fire testing facilities at universities on the West Coast of the United States. So we would be it. And we'd get to work collaboratively with all of you, continuing to do that and to further this industry. So I just wanted to thank you very much.